Have with us today Sasha Shlimovich, Shlimovich, sorry. From Technion. He's a PhD student working with Shlimovich. He's going to talk about data selection and empirical risk minimization. Some of you, I was just checking that with Sasha. Idan Diaz presented something that's somewhat related to this, but it's not the same work, so I'm even more interested in hearing what he has to say. So thank you, Sasha.
Yeah, thank you, Masha, for inviting me. Thank you for background presentation before. I didn't understand much because it was in Hebrew, but I mean, it was quite good. The pictures were better than mine, at least. So yeah, today we'll talk about data selection for empirical risk minimization. It's a joint work with Steve from Purdue University, Shai, and Amir from Technion. So let me briefly try to motivate the questions we were asking in this paper. So yeah, why at all we want to study data selection? So we can generally think about learning as some union of algorithm and data that we are trained on, right? So we all of the time, more or less, we have some algorithm, we have some data, and we want to try to optimize our algorithm to perform some task. Recently, like there was a lot of studies that were trying to focus on data because in the beginning, mostly people were thinking about algorithm and data was considered just under ID assumptions or some other assumptions. And we here try to do a complement approach where we more or less consider some simple algorithms and after that try to think what data, what parts of data suit most the algorithms that we are trying to optimize. Okay, so let me try to give you first, I mean, this was probably during the background, but I will briefly repeat. So hypothesis, so what is empirical risk minimization is generally if we have a hypothesis class and we have some data set, then H is empirical risk minimizer if it minimizes the loss over this data set, where the loss we can define as loss of any point, taking some of these losses and average it over n. Okay, and yeah, important part is that sometimes it is not just one hypothesis. Sometimes we have many hypotheses that minimize this error, and each one of them is empirical risk minimizer. Okay. So let's first phrase like the most general question we can think about in our setting is, okay, is all data equally useful for solving a given learning task? Okay, so and let me show you an example that answers these questions. So okay, so suppose we have a learning task of finding the point that minimizes maximal distance to the points of a data set, and our data set is supported on R. Then what do you think about whether or not this point is like finding this point depends on the whole data equally, right? So the answer is no. That basically our answer will only depend on the two furthest point in each direction. Okay? So it doesn't matter whether our data set has a point y2, y3, or any other point in between. The output will only depend on furthest point, right? This is a simple example where the answer to the question is no. Not all data is equally important. Okay, then let us refine our question. So, is it possible to select a small informative subset of data that still guarantees good learning performance? As in previous example, it was possible to select just 2 points, and our algorithm will perform the same on this dataset, right? So for each dataset supported on the line, you can find 2 points that will output you exactly the point you want. So let me try to show you our framework first in informal and then informal way. So generally, learning will look like we have a data set, we train on this data set some algorithm, and we output a hypothesis, and we evaluate it on the whole data set. And yeah, in this talk, I will say that data set is just a finite number of points, but if we increase n, it can approximate any distribution. So I don't want, like, sometimes I will talk about distributions, but most of the time I will talk about just the data set of points. Okay, so if we have a data set, we train on it, we find an optimal hypothesis. So in terms of ERM, we find an ERM, and we evaluate the loss of this hypothesis on the whole data set. Okay, now I'm asking, what if we select some small subdata set of this data, we train the same algorithm, so we apply it, like previously we applied this algorithm on the whole data set, now we apply it on the small subdata set, and we output some hypothesis, but we still want to understand how good this hypothesis with respect to the original data set. So we evaluate this hypothesis not on the subdata set S, but we evaluate it on the whole data set D. Okay? Does it make sense? Okay, good. Okay, so, and formally, we were interested in such question. So, what is the optimal selection of this subdata set from the previous slide? So we have a data set, we have some fixed and known learner, and we want to select the best possible subdata set of the data that our output of the algorithm will have the closest possible loss to the loss that was trained on the whole data set. And to abstract it, we introduce a teacher. So the teacher, he knows everything. He knows the data set, original data set. He knows the algorithm that we are trying to apply. And the teacher has unlimited time, and we do not care about whether or not we can calculate the subdata set efficiently. And we just ask the question what this teacher should provide to the learner in order to, if we restrict teacher to only provide S of size k. Okay?
Right. The teacher knows the underlying distribution?
Right, right. So here we think that our data set is the whole distribution. And teacher knows it. So teacher knows everything. And he just tries to select the best possible subdata set in order to learn. Okay, so this question, so this framework will give us the answer to the question which part of the data set of the distribution are the most important. So how, if we have just a budget of size k, how to find the most efficient way to learn this task. Right, this is closely related to sample compression schemes and yes, for course sets, and I will discuss it a little bit further later. And so basically, we try to find the small informative subdata set here. Okay. Any questions here? Right. So let me then briefly tell you what we studied. In this talk, I will mostly focus on mean estimation and linear regression, and but generally we studied this question in many settings. So in order to define a setting, we need to define a loss function. We need to define a learning rule, right? So as you see, all the learning rules here are ERMs. Maybe for mean estimation, it's not obvious from the naming, but we will discuss it now. And right, so sometimes you can see that we select mean norm ERM, max margin ERM. It's because, as I previously said, there can be many possible ERMs for some learning tasks. And you can ask this question for any ERM. You can ask this question for some particular ones. These are the most standard ERMs for these tasks. Okay, so let's continue with mean estimation. So our task is, okay, so we have d points. This is mostly for everybody to feel what is happening. Okay, we have d points in Rd. We want to select subdata set of size k. So it can be any multiset. We can pick some points twice, 3 times, doesn't matter. We just want to select some subdata set such that what happens. Okay, so our loss of hypothesis of any output. Yeah, so and our goal is to output a point in Rd, right, which will estimate the mean. Okay, so right, loss is just average of square distances to all the points in original dataset or in original distribution. And the optimal solution is just average of all points, okay? And if we think about distributions, then it is not an average, but integral over the distribution of a point. Okay, and we define optimal loss as the loss of optimal solution, and we ask a question. Okay, so for hypothesis that we get from sample S, our hypothesis will be just an average of points in S, right? Because in the setting we fix the learning in advance, so the learner A is fixed, and the learner outputs just an average of the points. Okay, and then the optimal loss for K size multiset will be minimum over all possible subdata sets of size S, of size K, of loss of this outputted hypothesis. Okay, so this is the best we can get with selecting subdata set of size K.
I think you referred to this earlier. Wouldn't it be more natural to define L in the bottom as the expectation over the true distribution rather than the fixed D?
Right, so I was saying that here I focus on dataset D, so you can think of it as an underlying distribution. And since our the whole framework doesn't really depend on the size of the original distribution, right? It only depends on the size of data points we can select. Then we can think of D.
Yeah, so yeah. That's what he said. He doesn't care. You can increase.
Yeah, right. And we can increase D, and we can approximate any distribution you want with this finite size data set. Okay, so right. So let's consider the simplest possible case. We can select just one point, and yeah. So the question is that we want to answer is what is the largest possible deviation of our optimal loss for subset of size 1 with respect to general optimal loss. So this is loss at point average of the whole data set, and this is this formula that we defined in the previous slide. Okay, so when we consider just one point, then we need to check what is the loss of if we calculate, if we output just this point, this point, this point, this point, this point, and select the best possible loss over all these 5 possible outputs, right? And in particular case of mean estimation, it so happens that being close in distance to the optimal solution is being close in loss to optimal solution. Okay, so that's why if you are thinking about, okay, what is the optimal solution will be the closest point to the average, which is I think it was expected. Okay, and after that you can, from some probabilistic argument, you can derive that the optimal loss will be at worst case twice as far from the optimal loss over whole data set. You just take an expectation over selecting randomly these points, and you will get exactly 2, and then you can pick one point which will have the loss 2. So this is the easy case. So let me try to show you what is going on after that. So, right, for k equals 2, we need to consider not only 5 points of our data set, but also all middle points of selection of 2 points. So in this case, we need to consider 5 points and also 5 times 4 divided by 2, and also 10 points that can be in the middle, right? And once again, your optimal solution will be the closest point to the average of the whole data set. And on this picture, you can see that it doesn't really depend on whether or not the 2 points are close or far from the optimal point. Right. Well, because I allow multisets, I also can get these points, these 5 points.
So you could do more.
For 2, I can do only.
2. K equals 2.
For k equals 2, I can do only that. Right. For k equals 3 and 4, yeah, I can get some divisions of this point. All right, and in full generality, we don't even know like answer to this question. Okay, that's what I wanted to stress out. That actually this problem seems very easy, but even for d equals 2, we proved it, but it required some technicalities, and it's not generalizable to d equals 3 already.
So would you know about this number?
I will tell it in a couple of minutes. Okay, so I wanted to tell one approach to how you can tackle this problem. So just as a background, there is a Krasnodary theorem, and this theorem tells you that if you have some set of points in RD and you have some point in a convex combination, then there exists some other subset of X of size d+1 such that X is still a convex in convex hull of these points. And in R2, as example, you can always find a triangle that will capture the point inside the set of any numbers of points. Okay, so this is Krasnodary theorem. It's not very involved, I think. Okay, so right, what can you think about? Okay, you know that LD star of 2 depends on just 2 points, right? So you know that in this particular case, maybe you have just 2 points that give you LD star of 2. So most of the points doesn't really involved in computation of this. So you can think about maybe you can select some smaller subdata sets with which will still have the same, which will witness the same ratio of optimal of 2 points and optimal over the whole data set, right? So that you can maybe delete some points from your original data set and consider smaller problem. And it's actually the case, but it's not enough to just apply Krasnodary to get the data set of 3 points here. Because you also need to think about what is in denominator, right? So when you change the data set, you also change the optimal loss. And in order to handle it, we needed to refine this classical cross-ordering theorem and to formulate cross-ordering for convex function theorem. Okay, so what it is you have set of d+1 functions, right? If you have some set of convex functions, then you can select, right, and you have average of these convex functions will always be a convex function itself, and you have a minimizer of this convex function. So this is the blue line, which is just an average of red lines. Then you can select just d+1 functions such that you will have as an average of them the function with the same minimizer, and also like this will be just some straight application of cross-ordering on on this function, but you can also carefully do so such that the value at your optimal will be smaller than in original. So you can always do it in such a way that you decrease the total error. And that actually allows you to reduce the number of points here to 3 points, because you carefully look that this optimal loss here over whole data set will decrease, which can only increase your ratio. And that's why if your argument, your bound will work for the data set of 3 points, it will also work for data set of any points. This is like the general approach how you can do it. But I want to say that even here, like after you do it, like for d = 3, it's still hard to understand what is the answer. I mean, I have a hypothesis of what the answer is, but I don't have a complete proof for it. Okay, so
just to make sure, you're trying to approximate the center of gravity of the original set, the
right.
full set.
Right.
So although you threw away some of the points, they still affect what it is that you're trying to do.
Yeah, but we delete these points in such a way that the optimal solution will remain the same, and we decrease the loss over the dataset. So the loss over this new small dataset.
So if you use Carter-Dory to re-express the center of gravity of everything as a center of gravity of d+1 points?
Mm-hmm.
Okay.
Yeah, and we also...
So what do you know about, I'm asking you again, so what do you know about this number?
Right, so here, what we know, so we know that for d equals... yeah, for d equals 1, we know the answer to everything. So on d equals 1, it is not so easy, but you can show that it is 2k over 2k minus 1. And for larger d, we basically just know the asymptotics and for large d's, and basically just the number here. So basically, even for this problem, it is quite hard to find the answer.
So 1 plus 1 over k. Here, both d and k go to infinity. Right?
Yeah.
How?
No. K is fixed, and you k fixed, and you move d to infinity, and this result is basically saying that when you increase d to infinity, it doesn't matter. So all the points will be equally non-informative to you. Like it's what you will get from just a random sampling.
Is the proof of the generalized Carter-Dory theorem constructive, or just that exists?
So it is basically follows the proof of Carter-Dory. So one of the proofs is you select that you basically have right. So yeah, it is constructive. It just follows the constructive proof of Carter-Dory.
It's not a difficult theorem. Yeah. One of the 3-4 first theorems that you prove in complexity.
Yeah, right. Okay, so let's move to a little bit different setting where we know a little bit more. So, okay, one thing to relax. So generally it was quite hard problem. So one thing to relax is to allow not select a data set of k points, but to select a support set of size k, and that's where you will notice that this is a course set basically. So you want to select a course set of size k, and so your teacher will output not data set, but some distribution over k points. Okay, so you have a data set of points in RD times R. You have a your teacher selects some support set of size k, selects some distribution over it, outputs it to learner, and learner optimizes this error and finds W that minimizes it. Okay, so let's consider this setting now. Okay, so for k equals 1, everything remains similar. You still get it as just probabilistic argument and averaging over selection of any point. Okay, for k equals 2, in the particular case, you already done. This is what differs selecting a sub-data set and support set, because now you can allow any distribution, and you can always tune this distribution in such a way that you will get optimal error, right? So you can take these 2 points and you can change the distribution over them in such a way that your line will be exactly what you wanted. Okay. Right, so for linear regression, then we know that if k is larger than 2D, then this number is equal to 0 or to 1, and for k equals d plus 1 and d plus 1, so in between, we also know that it is bounded between 1 and d plus 1, and for small k, you cannot get any guarantee. Okay. And we know a little bit more, and I will. Yeah, and I will explain when and how. Okay, so first let me explain why 2D, because it seems a little bit weird that we have this gap at all. So, and the example here is that another generalization of Karassi-Deodary, or not generalization, but different case, is if we are really care about the fact that the point is inside the interior, then in Karassi-Deodary theorem, we no longer need d plus 1 points, we need 2D points. And one way to see it is selecting 4 points that form a square. And you notice that if you pick intersection of diagonals, then deleting any point will move your point to the boundary. So you can still apply Karassi-Deodary, and you can find 3 points such that it's inside a convex combination, but you can no longer guarantee via just Karassi-Deodary the fact that it will be inside the interior of the output. Okay. So, and why it is important in this case? Mainly it comes from the fact that the loss function we have is not strictly convex. If it would have been strictly convex, then we can do for d plus 1 already 1 and everything works. But since it's non-convex, you can think about this example. Okay, so we have this data set and we select just 3 points from it. Then our hypothesis will overfit for, so let's think we do not pick the point e to 1, then our hypothesis will overfit to this point, right? And we will get some positive error here because our 2 directions are separated, and basically we have 2 learning tasks on each of the dimensions. And yeah, so is this construction clear?
Question?
Yeah.
You mean here that x star is x size to b?
Right. X prime as a size. So X prime, right. Right. So type. Okay. So what we actually know in this setting, so we know a little bit more than what was on the previous slide. We know that for k equals 2d minus 1, it's actually 1 plus 1 over d. And I will now explain why here we have d and here we have 2d minus 1. And we'll also explain, like, define the picture in between and why it's hard to tackle. Okay, for k equals d, error d plus 1 also follows from probabilistic arguments, so you can understand that in most of the cases we know the answers. It's because you can construct some distribution and you can bound expected error over some subdata sets, and after that derive the fact that the worst case error should be at least expected error. Okay, and but here you do not sample them uniformly. You use volume sampling. That is from work of Dzerzhinsky and Varmov. And the idea of volume sampling is that you select each subdata set of size d with probability proportional to the volume of of convex hull of this subdata set. And important part about this volume sampling is that it doesn't depend on what are the values, but it allows you to still derive such an error. And this is, like, I suggest reading this work. So it has many interesting properties. It's so the estimator of W is unbiased. So this property over the error and some other properties as well. So it's a genuinely interesting way of sampling, and it allows you to derive this bound. Okay, for 2d minus 1, what you can prove is 1 plus 1 over d, and I will briefly explain how you do it. So you can ask a question when you can't learn the optimal error with just 2d minus 1 points. And the answer is that you need some similar construction to the one that witnesses the need of 2d points in this Stein's theorem. And this construction can only look like pairs of points on d linearly, no, not actually axes, but on linearly independent directions, and 2 points on any of them, and deleting 1 point will result in the fact that on this direction you will get some loss. So
why can't you do the same construction so that 2d minus 2 you will have two directions that are
right? I will explain the problem there. Yeah, so here you do it for right. So okay, and let me briefly try to explain why you will get an error d plus 1 divided by d. It's not so hard. So you have, let's just think that any construction we have is just axis parallel, 2 points, and we delete one of them. Then when we delete this 1 point, we will get, so suppose we had originally error over this direction equal to L1. After we deleted 1 point, we will get the error over this direction equal to 2L1. Okay? It's also a very easy computational task to understand. And after the teacher can select this direction in the best possible way, the one that he will force the error on. Okay, but we have d direction, and we will select the one with the smallest error over it. And in the worst case, they will have this similar error. And that means that you will at most get d plus 1 over d because you increased one of them to 2L. and sum of all of them was DL. Okay. Yeah, so right. Okay. Yeah, so let me right. Why we cannot apply the same argument to larger is basically because there are different several constructions that will result in in our non-ability to learn from k equals 4 points. Right. One construction is still the Steinitz type construction. So, like for example, on if we have 3 dimensions, we will get this construction where we don't pick 2 points on different directions, but also you can think of different constructions that result in that, and like one simple of them if you have just 3 points on a plane and 2 points on a line orthogonal to it. But it's not the only construction that can result there. We know the description of the constructions that result in the errors, but it is not easy to understand what are the optimal error in any type of construction that you can get. Okay, yeah, so we can generalize these 2 settings and ask the general question of whether or not linear some linear W over some domain with some loss function will be learnable. So, and this setting will capture both the mean estimation and the linear regression. But it's also interesting to understand in full generality what happens there. Okay, so if I still have time, yeah, I still have time a little. Okay, then I will probably tell you a little about linear classification. So linear classification case is you have a data set over RD plus minus ones, and your loss function is just a classification function. Okay, and you consider max margin classifier. Then the picture becomes quite easy, and you know that for k larger than d, you can achieve perfect accuracy, and you can guarantee no accuracy under k smaller than smaller or equal than d. What do I mean that you can get no guarantees? That this error can be arbitrarily close to 1/2. And yeah, the construction that captures it is basically the same constructions that you will get from stable sample compression for max margin classifier, which is like the fact that for max margin classifier you can select d plus 1 points such that whenever this d plus 1 points in a data set, you will recover the exact classifier that classifies it. This is called stable compression, when like, no matter data set, if which subdata set of data set you take, if you have this particular d plus 1 points, in this case, these 3 points, you will always recover the exact same classifier. Okay, and I think that's it. Yeah. Right, so do you have any questions?
Yeah. So there's a easy version of this problem where instead of optimizing over the small data set, you just take a random. I think that's it. Is that easy?
If what again?
So I take 2 points, but I choose them randomly. I don't try to find the best.
All right.
And so the ratio of the loss I get with a random set of points and the full set of points, that should be easy to compute.
Yeah, and Yes, that's generally true, and in our work we also compare this result with, you can think of what we do is studying the worst case possible, where we pick the best possible data set, right? So we pick the best possible data set to, so the teacher is allowed to select some optimal subdata.
So how much, that's my question now, is there a constant factor between the best possible one and just the random one?
Yes, so for example, for mean estimation, if you consider just random selection, then you will always get 1 plus 1 over k. Okay. So for any k, for any d. And so,
what? So everything is bounded between 1 and 2, all the ratios in this example. Like
yes.
The maximum ratios.
Yes. And yeah, so here you know that.
So bad.
No, but what I don't understand.
Yeah, so here you get exactly the same answer, right? Here you get exactly the same answer, but here you get, like, instead of 1 plus 1 over k, you get 1 plus 1 over 2k.
But here, I don't understand. Even in the one-dimensional case, right. The first example that you gave,
right.
To find the center of gravity.
Mm-hmm.
If you have many points here and one very far, if you sample, you won't see it. And it affects the outcome tremendously. So it's not that, in general, you cannot expect that a small sample will. Working with a small sample is not necessarily, maybe a very bad approximation.
But in that case, also your original loss is terrible, and he's talking about the ratio.
Right, the one reason
so the ratio will be still a factor 2 at most.
It's like in k-means clustering, we know that if instead of finding the best, in doing clustering, we just choose k-needling. So if you just randomly choose k points, I think it's a factor of 2 from the best that you can do. So it's often the case that optimizing is only
yeah, and actually
takes it so far. So here, I guess it's like that. It's between 1 and 2, and so that I'm not sure you can convince a practitioner to start optimizing.
Right.
But
he keeps using the data set as the ground truth, but I think that the theoretical question is more about, like, if God could sample from a different distribution instead of just from the original distribution, what would he give you in order for you to learn something better? So, like, switch perspective to having the full data set as the underlying distribution, and the oracle being someone that gives you a subset that is, like, somehow more informative.
Right. Yeah, and the insight is, like, what parts of this data set are actually helpful for you.
Yeah, it's actually a question about compressibility. Right. There is a teacher. There is no teacher. The question is, does there exist such a small subset that represents the information that you use?
Yeah, and the confusion about losses, I think, like, that is main reason why here we use the ratio is because generally this loss can be unbounded, and so one natural way is, okay, we can bound over all data sets that give you a loss not larger than some constant, and you can try to find this one, so the minimum over all possible data sets that give you that minimize this loss. But we decided to go with the ratio instead of it. So there are different natural ways how you can approach and what you want to bound here.
Honestly, I haven't understood you. You had this business with the context function.
Right.
Yeah, this. Can you state this? First of all, the functions, I think when you said the functions were convex. But you don't
yes, strictly convex.
The
important part is that they're strictly.
Okay, so these are convex functions from R D to R.
Right.
And then what is the statement?
The statement is that if we have n functions from Rd to R that are strictly convex, strictly convex. For us, strictly convex is important because when we take some convex combination, it will still be strictly convex. Okay, so we have only one minimizer over. Okay, we take strictly convex function. We take their convex combination, which is the blue function. Then we can
just an average.
Yeah, okay, just an average. Then we can select d plus 1 of the functions
and average them.
And not average, but as a support again. With weights.
Okay.
Such that we will get
the minimum of the smaller thing is happening in the same
in same point, and also have a smaller value.
So that's a new result, or this is something because Carter-Dori is from over 100 years ago?
Yeah, I mean, I don't know whether it was strictly stated in this particular setting. I guess like the fact that it is just the same minimum is just a straight consequence of Carter-Dori, but in order to also capture the fact that here it is smaller, you need to carefully apply this Carter-Dori argument there. So it's still the same argument as in Carter-Dori, applied to the gradients at this point of all the functions, but you need to carefully understand it.
Did you consider the sort of opposite question of can we understand what is the maximal, I don't know how to think about it, like sensitivity, or maybe it's some version of Tukey depth, which is like if I have some set of d points, endpoints, and there's like some in a fixed case. So here's this optimal subset. How easy it is to change the full set of endpoints so that a specific point will no longer be critical. So, right, if I can imagine, let's say if it's in the linear classifier, so if I have many points along the line, along the margin, or very close, then it's very easy to get rid of each point, maybe. Versus in some cases, no, this point is very hard to get rid of unless you do something extreme. I'm trying to think from the sort of sensitivity perspective of
yeah,
what does this mean?
we didn't study this question. I guess our question is really complementary, right? We think about the worst case, the most sensitive in most of the cases. Yeah, we thought a little about Tukey depths and what we can say is there, but basically no particular results that we can share.
That's privacy. This is
begs
the question now.
Thank you very much.